Let's go quickly to the next speaker, John Lienhard. John is the Samuel C. Collins Professor of Mechanical Engineering, and he's soon to be the Director of the Water and Food Security Lab. And his work covers a variety of techniques for providing potable water, from desalination to remediation and recycling. And today, John will be talking about solutions for water supply.
Thank you. Thank you all. I'm afraid that was a tough act to follow. But I'm going to speak about solutions for water supply. It's a somewhat grand title, and so I'll tell you the punchline now. If I were to give you a menu of items that we might consider to address the world's water supply issues, whether it's policy, economics, governance, reuse, conservation, desalination, the answer is all of the above. I'm going to focus today on a particular subset of this, and I'll talk primarily about technological solutions for providing water, principally to urban settings. So the graph that I have here is a chart that compares the renewable supply of water in an area, which is the difference between precipitation and evaporation over land, to the human withdrawal of water. And in regions where you see red spots, those are regions where the withdrawal of water is approximately the same as the renewable supply of water. And so what you'll see immediately is that regions where we have this kind of water scarcity are found throughout the world, on essentially every continent. They're found in the developed world, they're found in the developing world, they're found in regions that we might think of as traditionally being arid or dry, perhaps the Gulf states or North Africa or the Western US. But they're also found in regions that are relatively wetter, parts of India and other areas, even Florida. And so you see that this is a problem that is diverse in its context, diverse in its causes, and will have different solutions every place you look. One other observation you can make from this graph is that many of the regions that have water scarcity are regions where you have relatively high population density. A lot of people live there, so there's a lot of demand for water. You'll also notice that many of these regions, Southern California, for example, northern China, are regions where you've got large cities near the sea, near the ocean. And you'll also notice, with some surprise perhaps, that places like sub-Saharan Africa don't appear on this graph as having water scarcity, when in fact they do have serious water problems. But the water problems there are driven more by lack of infrastructure and economic limitations to providing water supply, which hold down the consumption of water relative to what's available. Now, what's driving pressure on water? This is a graph of world population. I'll start in about 1960, because that's roughly when I was born. And the world population was about 3 billion people. Today, 50 some odd years later, I won't say exactly how many, 52 years later, the world population stands at 7 billion. And there are forecasts for where it will go, depending on which scenario you use. But the likely idea, the likely projection is it will be at about 9 billion by 2050. And since I'll take an optimistic viewpoint, I can say that during my lifetime, world population will roughly triple. All those people are going to be fed from the same renewable supply of water. We don't really have the means to drive water supply from rainfall up by a factor of 3. And from talks we've heard earlier today, we probably wouldn't want to. So we're going to have to find solutions to provide for this population from the renewable supplies that we have now. And we've done a lot in that direction. This is a map showing the Colorado River. You'll all be relatively familiar with what's illustrated. At the Glen Canyon Dam, the 100-year average flow is about 500 cubic meters per second. I'll use cubic meters a lot today. A cubic meter is about 1,000 liters. Well, it's exactly 1,000 liters. But if I move back into those other units, it's about 265 gallons, whatever a gallon is. And by the time this river gets to the northern international border with Mexico, only about 10% of the water remains, because it's been diverted to cities all along the way. It's being used also for irrigation and other purposes. In some years, by the time we get to the southern border with Mexico, there's no water. And most years, the river doesn't really reach the Gulf of California anymore. So already there's been a very severe impact of our quest for water on the environment associated with this river and on the economics of anybody who might want to do farming down by the delta. A more dramatic example comes from Central Asia. This is or was the Aral Sea. It was 68,000 square kilometers. This is a picture of it in 1989. Here's what it looked like in August 2009. And what's happened here is that the two rivers that feed the Aral Sea were diverted in order to grow cotton in Uzbekistan. It's actually a process that began under the Soviet Union, but over time the Soviet Union broke up, the management of the river system changed, and this sea is gone. Along with all the fishing villages that used to be here, the livelihoods of the people there, and also with a very large impact on local climate. It is now dusty and much hotter because you haven't got the capacitance of the sea to regulate the temperature. The way people use water varies quite a bit. Some of it has to do with the ease with which they can use it. Some of it has to do with how water is priced in different places. The photograph on the upper corner there is a fellow in Long Beach, California, cleaning a sidewalk. He's cleaning his sidewalk with water that was brought to him through one of the aqueducts from either Northern California or from the Colorado River, and he's using it rather freely. This is a photograph that shows the way many people in the world obtain their water. There isn't good central distribution, so someone in the household has the daily job of going and filling a bucket and bringing it home. Usually, it's women and children who do that work. And this difference appears as well in the per capita water consumption in different countries. In the US, the United Arab Emirates, as two examples, we're using roughly 550 liters, 550 quarts, if you like, of water per person per day. That's excluding water used for agriculture. That's excluding water used to cool thermoelectric power plants, which turns out to be a big consumer of water. If you go to other parts of the world that lack the infrastructure, you find people are living on much smaller amounts of water. The UN considers this to be water poverty, and the impacts are quite clear. So this brings me to the question of what we're thinking about when we talk about purifying water. If you look at the spectrum of things that are in water, we worry a lot about bacteria and viruses. These are large items, it's a log scale. They're relatively easy removed by flocculation. Bacteria and viruses are easily killed by chlorine, which is cheap and inexpensive. And when you get down to looking at saline water, salt water or brackish groundwater, you're now looking at dissolved salts, much smaller things at an atomic level, and the technology to remove them is therefore significantly more energy intensive and complex. And so this brings us to the ocean. The oceans are an enormous supply of water, enormous body of water. It's 97% of what we have on Earth, roughly. It's about 3.5% salt by weight, salt being not just sodium chloride, but also things like calcium and carbonate and sulfate and so on. And this body of water, of course, sits near a lot of cities that might wish to take advantage of it if we could make it drinkable. So what is desalination then? Desalination is the removal or the separation of salts from saline water to produce potable water, water that you could drink. And this is a thermodynamicist understanding of a desalination system. Seawater comes in, fresh water comes out, concentrated brine comes out. And in order to provide the work of separation here, some type of mechanical work or electrical work has to be applied. And so this, in essence, is what a desalination system does. It unmixes stuff. The energy requirements of these systems are pretty well defined. Thermodynamics will tell you that the best you're ever going to do is about 1 kilowatt hour per cubic meter of fresh water produced if you are working against seawater. Today's best systems will do this for something like 2 to 4 kilowatt hours of electricity per cubic meter. If you want a benchmark to compare that to, think about pumping up groundwater. To bring groundwater up through a world average lift of about 120 meters, that's about 0.6 kilowatt hours of electricity. Now, systems of this sort are routinely deployed. It is getting to be relatively off-the-shelf technology. This is a system that we saw in Copiapó in Chile. It sits in the Atacama Desert. It's actually something that we visited in the course of a MISTI project. That's a photograph of the region outside the city of Copiapó. It is the world's driest desert. In some portions, they have never recorded rainfall. Water is mainly coming from runoff from the Andes behind the desert. The desert is coastal. And so Copiapó is a city that's driven by the mining economy up in the Andes. And the miners need a lot of water for rinsing rock and for other things they do. And so a lot of the water is being drawn off for mining upriver of Copiapó. The Copiapó River has been dry for 15 years. A lot of water is also being taken for agriculture. You can grow grapes in the desert here. You can grow grapes in the desert there if you irrigate enough. And the grapes apparently are very plump. They're shipped to Japan. They sell for several dollars a piece. So it's a good market. Water rights are also over-allocated, about a factor of 6 relative to what's available. And Copiapó has been forced to go to groundwater supplies that are saline. So they have brackish groundwater. It's about 0.3% salt by weight. And they are purifying it using reverse osmosis plants, particularly the one that's shown here. So this brings me to the separation process. What's going on? Well, desalination plants of this sort are using membranes. The membranes are impermeable to salt, but water can pass through. And what's done is to pressurize saline water on one side of the membrane. That forces water through to the pure side, overcoming what would otherwise be the osmotic tendency for water to go from the pure side to the saline side in a quest for equilibrium. And in this particular case, the pumping is being done by the pumps you see in the foreground. These are running about 9 bar, 9 atmospheres, given the relatively modest salinity of the water. The membranes are spiral wound. They sit in canisters of this type. This is about 1 meter by about 8 centimeters. And they are stacked up in these pressure vessels behind. And the end result is that you get purified water. So this is representative. More classically, desalination has been done by distillation. This goes back to antiquity, boil water. The water is volatile. The salts are non-volatile. They remain behind. You get a brine and water vapor that you condense to give you pure water. In fact, that's what our atmosphere is doing for us. That is our renewable supply of water. We can replicate that. As engineers, we're actually very good at doing this in an energy-efficient way. But as you'll see from the numbers here, the best we're going to do, according to thermodynamics, say 15 kilojoules of thermal energy per liter of water. On the other hand, our systems that we've built are requiring 20x that amount. Why is it 20x? Well, it's mostly because to get better energy efficiency, you need smaller temperature differences, means you need bigger heat exchangers, means you spend more money on copper piping, means the capital cost goes up, means that the economic optimization of the system is not toward energy efficiency, it's toward the dollar cost of water. And so they don't design them to be terribly efficient. Electrically, if I were to use the steam that drives this process to make electricity, this would be on the order of, say, 14 kilowatt hours per cubic meter, which is to say substantially less energy efficient than an RO plant. So where do we look? If we look at the spectrum of technologies that are deployed today in desalination, reverse osmosis, the membrane processes, represent about 2/3 of installed capacity. It represents as well about 81 million cubic meters per day of installed capacity. That is equivalent to about 6% of the world's domestic water consumption. Not all of it's used domestically, some of it is industrially used. It's equivalent to about 0.8% of what's withdrawn for water supply. Of this, about half is seawater desalination. Takes less energy, costs less money to desalinate brackish groundwater. So if you can find an aquifer that's mildly saline, you desalinate that before you do seawater. Almost all of the seawater, well, almost half of the seawater capacity is from these old thermal technologies. These are mostly large legacy plants, mainly in the Gulf states. They have very long lifetimes, maybe a 40-year working life, and so they're not going offline anytime soon. Most of what's being built nowadays is membrane-based. Turns out the U.S. is actually one of the largest desalinators of water in the world. We're about number 3 if you look at installed capacity. You just don't see it because we're such a big country, and we're talking about a few percentage of our consumption. You'll find it in Florida. They're restarting the plant in Santa Barbara. There are a number of other projects. Now, how does this compare to other ways of getting water? If we look at California, I mentioned the aqueducts before. So San Diego County down here is importing about 80% of its water. It's getting it about half from the Colorado River, about a quarter or so from Northern California. And if you look at the energy costs that go with pumping that water from one end to the other, bringing water from Northern California down to Southern California, it's around 2.6 kilowatt hours per cubic meter. That's without any treatment. That's without the high-pressure service in the city. It's about the same as what it would take to desalinate seawater directly on the coast. And it would do that without then getting into the water wars about who gets the water in the river here, without depleting Colorado River, et cetera. So there's a lot of discussion around desalination in California. The other issue, of course, is that aqueduct transfers are not drought tolerant. If the drought happens to be occurring in the region where you're taking the water, you're going to suffer as the source region suffers. And so there are some issues about aqueducts relative to desalination, which just runs steadily. It's not susceptible to drought. What is the other side of this technology? Well, one part of it is that you make a brine, right? You get a very saline wastewater to be disposed of. That saline water contains typically twice the salt of source seawater, if you're doing seawater desalination. As a result, you worry that when it's put back in the ocean, you'll produce regions of locally high salt concentration, which would be inamicable to things that live there. What they've done in Perth, Australia, is they've taken the discharge about 500 meters offshore. They have a region of about 20 acres over which they've distributed a number of nozzles of this sort. So this is one of several dozen of these. And the water is, saline water is re-injected into the ocean. Now, I should point out, the brine is not normally purple. It, in this case, contains rhodamine dye. They were required to do a verification of the dilution of the water, the mixing zone of the water, to compare to their numerical models. So they did a dye test. They found very good agreement with the models. So the salts can be dispersed. What else do you worry about? There's some residual chlorine. It has a very short half-life, maybe 15 minutes in the ocean. More significantly, particularly with the thermal plants, might be corrosion byproducts, chromium from the heat exchanger systems, for instance. It's a bad thing to have in water, and so those types of byproducts need to be considered as well. I got this slide from the fellow who designed the plant in Perth. He had spent many years on it. He was delighted to point out marine life on the diffuser ports as well. What else can we do? Well, recycled water is another area of a great deal of, that's getting a great deal of attention nowadays. And by this, I mean taking wastewater, i.e. sewage, or as they call it in Singapore, used water. Okay. Taking used water and purifying it enough that it can be integrated into your potable water system. It's routine to take wastewater and use it for irrigation purposes or for landscaping. That's not unusual. But getting to the point where people will drink it is another story. Why would you want to do this in the first place? First, you're reusing water that you've already got. You don't need to go get new supply. Second, it takes less energy to purify water this way than it does to desalinate ocean water. And so you have a more energy-efficient approach. In Singapore, they've been very aggressive in implementing recycled water. It's 30% of their demand now. They're aiming for 50% by 2060 when their water contracts with Malaysia expire. Most of this is going into factory use, industrial use. Some is blended into their primary reservoir. And then a fair amount is distributed in these water bottles at public events, soccer games, to promote acceptance of used water as an appropriate source. But it's not just Singapore. There are a number of reuse projects active in the U.S. and on the drawing board in the U.S., particularly for non-potable use, I should say indirect potable use. What does that mean? Indirect potable use means you blend it back into a reservoir. You don't put it right in the pipe so it's mixed up with stuff. You inject it into your aquifer where you're drawing the drinking water so it's mixed up. If you ask people why they won't drink recycled water, you often get to an argument that has something to do with it going to ground. And it's an interesting paradigm, an interesting puzzle. It's not one that I, as an engineer, am best qualified to answer, but it's a very important issue in social science as well. So I'm going to begin to wrap up here. There's a heck of a lot of work at MIT around water technology. Far more than I could talk about in a short presentation today, far more than I could talk about in an hour. Number of things that have happened. There's work, the Gleason group has got anti-fouling membranes, bacteria won't grow on them. Professor Yusuf Toomey, Professor Whittle have been working on leak detection and water distribution networks. Professor McKinley has made membranes that'll separate oil from water, which is good for various types of industrial activities. Professor Berger has been very active in redesigning, reconstructing wetlands to improve their function and renewing water supply. We have work by Professor Entakabe that's on remote sensing, determining how much water is in a given region, and also several groups working on graphene membranes for water desalination. So it's a very active area. Leak detection in particular is important because most municipal networks leak 20 to 50% of the water put in. Yeah, it's very, in the US, typical number is 20%. If you go to the developing world, it can run to 100% if there's piracy. And so detecting and controlling leaks is actually a very effective way to deal with water shortage. If you have a network that's leaking 50% of its water, and you can plug those leaks, you've doubled your ability to provide water, right? If it's economically doable. So the last thing that I'll mention, and Rob, this is my final slide, is that we have recently started a major effort at MIT to undertake problems of water and food from all dimensions. Through a gift from Muhammad Abdul Latif Jamil, who's a civil engineering graduate from 1978, we've established an institute-level laboratory on water and food security. And this lab will be taking a multidisciplinary approach to looking regionally at problems related to providing adequate amounts of water and adequate amounts of food to the world's surging population. So I'll thank you and stop there.